In the vast dark between the stars, a question lingers: are we truly alone in the universe? Today, that ancient mystery is no longer just science fiction, but a rigorous scientific pursuit, driven by telescopes, probes, and careful data. Today, scientists scan the cosmos with vast radio telescopes, listening for even a single artificial whisper. Robotic spacecraft sample distant planets and moons, while biologists probe Earth's strangest microbes to learn how alien life might survive. When scientists say aliens, they mean any life beyond Earth, from single-celled microbes to complex multicellular organisms. Intelligent civilizations with technology are only one possibility, and are probably rare compared with simple microbial life. So modern astrobiology does not chase flying saucers. It focuses on detecting any biology at all: chemical traces, microscopic fossils, or living cells on distant worlds. To scientists, life means systems that grow, use energy, and maintain their inner order. They must sense and respond to their environment and evolve over generations through natural selection. These traits give scientists a checklist, guiding telescopes and space probes to search for worlds where such living systems could exist. Scientists now search for two main kinds of alien clues: biosignatures and technosignatures. Biosignatures are natural fingerprints of life, like unusual gases in a planet's atmosphere, while technosignatures are artificial signals or structures created by advanced civilizations. Our Milky Way alone holds an estimated 100 to 400 billion stars, each a potential sun for alien worlds. And the Milky Way is just one galaxy among perhaps 2 trillion in the observable universe, a cosmic ocean of possibilities. To find other worlds, astronomers watch distant stars for tiny, rhythmic dips in their light. When a planet crosses in front of its star, it blocks less than 1% of the star light, but sensitive space telescopes, like Kepler and TESS, can measure that shadow. From Kepler's data, astronomers learned that planets are the rule, not the exception. Most stars host at least one world. Statistically, there may be tens of billions of Earth-sized planets in habitable zones in our galaxy alone, with oceans and atmospheres potentially widespread. To estimate how many alien civilizations might ever talk to us, scientists often use the Drake equation. It multiplies factors like star formation rates, habitable planets, and the chance that life becomes technological, but each term is wildly uncertain. Its real power is not a final answer, but a roadmap that shows where our ignorance still hides in the cosmos. Mars is our closest promising target, a cold, desert world that once flowed with rivers, lakes, and possibly shallow seas. Today, its poles lock away vast caps of water ice, and salty brines may briefly seep near the surface in some regions. NASA's Curiosity and Perseverance rovers crawl across ancient lake beds, drilling rocks, and scanning sediments for organic molecules and other clues to past microbial life. Beyond Mars, 2 icy moons, Jupiter's Europa and Saturn's Enceladus, hide global liquid water oceans beneath frozen crusts. Gravitational tugs from their giant planets flex these moons, generating tidal heating that keeps their subsurface seas from freezing solid and may power deep hydrothermal vents. Enceladus shoots towering geysers hundreds of kilometers into space, and spacecraft like Cassini have flown through these plumes, directly sampling water vapor, salts, and complex organic molecules for signs of habitability. Farther out, Saturn's moon Titan hosts frigid lakes and seas, not of water, but of liquid methane and ethane. Cassini and Huygens revealed thick organic smog, hydrocarbon rain, and chemistry that assembles complex carbon molecules, hinting at a strange, methane-based habitability unlike Earth's watery recipe. These missions now carry miniature chemical laboratories, carefully tuned to sniff out life's fingerprints in alien dust, ice, and vapor. They hunt for specific organic molecules and telltale isotope ratios, like unusually light carbon or sulfur, that, on Earth, are almost always shaped by metabolism. Around the world, SETI projects point-giant radio telescopes toward the sky, searching systematically for signs of technology. They listen for ultra-narrow-band radio signals, sometimes only a few hertz wide, far more precise than any known natural emission. Radio and microwave signals are ideal for interstellar chat. They cost little energy to transmit and can cross light years with minimal absorption by cosmic dust. Modern SETI computers sift petabytes of data using algorithms to hunt for narrow, repeating patterns that stand out sharply from natural cosmic noise. Beyond radio, astronomers hunt for techno-signatures like nanosecond laser pulses, artificial flashes that would outshine a star for a single heartbeat. They also search for waste heat from hypothetical megastructures, where orbiting solar collectors could make a sun glow oddly bright in infrared. On distant exoplanets, spectrographs might even detect industrial pollutants, long-lived molecules like CFCs that nature makes rarely, but technology can flood into a sky. Despite decades of searching, not a single alien signal has been confirmed as genuine. Even the famous 1977 WOW signal, a 72-second radio spike from Sagittarius, has never repeated and remains officially unexplained, not proof of aliens. To claim contact, scientists demand a repeatable, independently verified signal that survives every mundane explanation, instrument glitches, satellites, even reflections from Earth itself. On Earth, life clings to boiling hydrothermal vents, where chemotrophic microbes endure pressures hundreds of times greater than at sea level. In acidic lakes with pH near zero, and in Antarctic ice below -20 degrees Celsius, extremophiles metabolize slowly but persist for millennia. As we look beyond Earth, scientists consider that alien biology might not mirror our own, water solvent, carbon-based chemistry exactly. Speculative ideas range from liquid methane or supercritical carbon dioxide as solvents to silicon-based frameworks under exotic temperatures and pressures. Yet carbon remains uniquely versatile for building complex molecules, and liquid water is abundant and stable on many worlds, so they remain our prime targets in the search for life. The James Webb Space Telescope does not take portraits of alien worlds. It dissects their starlight, splitting it into a barcode of colors. As a planet passes in front of its star, specific wavelengths disappear, revealing the fingerprints of gases like oxygen, methane, and water vapor in its atmosphere. Astronomers hunt for chemical imbalances, like abundant oxygen and methane coexisting, or complex organic molecules that are hard to sustain without active biology reshaping the air. In 2020, astronomers reported traces of phosphine gas high in Venus's clouds, a molecule on Earth often linked to microbial life. But reanalyses showed the signal might be processing error, telescope artifact, or unknown Venus chemistry, not necessarily life. Venus's phosphine controversy reminds us that extraordinary claims demand rigorous checks for contamination, calibration errors, and more mundane explanations before we even whisper the word alien. Astronomers estimate there are hundreds of billions of stars in our galaxy, and likely billions of potentially habitable planets orbiting them. With a galaxy more than 13 billion years old, there has been ample time for civilizations to arise, spread, and reshape the stars. Yet we see no obvious galactic empires, no engineered megastructures, no confirmed signals. a silence known as the Fermi paradox. Some scientists argue that intelligent, technological life is intrinsically rare, requiring a long chain of evolutionary accidents over billions of years. Others suggest civilizations flicker out quickly, wiped out by impacts, climate collapse, or their own technology, so the galaxy is mostly between pulses of intelligence. And some point out that we may simply be listening on the wrong frequencies at the wrong times, or for the wrong kinds of signals entirely. Despite decades of searching, we have only skimmed a tiny fraction of the sky for alien signals. In radio alone, our detailed surveys cover far less than 1/1,000,000th of the possible frequencies, directions, and times that we could listen. So the silence so far is not proof we are alone, only a reminder of how much cosmos still remains, unheard and unseen. In searching the cosmos for other minds, we are really asking, what kind of future is possible for our own civilization? Around a perfectly ordinary G-type star, our pale planet carries all known life, wrapped in a fragile film of air, scarcely 100 kilometers thick. Whether the galaxy is crowded with civilizations or silent and empty, the search reminds us that protecting this small, luminous world is our first and greatest responsibility. For now, we have no confirmed evidence of extraterrestrial life, only tantalizing hints and rigorous uncertainty. But a new generation of tools, like the James Webb Space Telescope, upcoming extremely large ground telescopes, and life-hunting probes to icy moons, will soon scrutinize thousands of distant worlds' atmospheres for chemical fingerprints of biology. Within the coming decades, these instruments may at last reveal whether life is a cosmic rarity or a common thread woven through the galaxy. So as we gaze outward, we also look inward, asking what it would mean to share this universe. Keep watching the skies and the data as the scientific search for life beyond Earth continues to unfold.